Greetings, my name is Matthew, and we are going to look at Chapter 9, Section 6, Focus and Directrix Definitions of Conic Sections, and we're going to be operating on the polar coordinate plane. And in this video, I'm going to walk through some PDFs, some slides, and this content is coming from Blitzer's Precalculus 3rd edition, so props for these pre-printed notes. And we'll look at some definitions and some diagrams, and then I will work out some problems as we go along. So without further ado, let's get started. The focus directrix definitions of the conics involved this E value, which is the eccentricity. And as you're seeing here, that if E is equal to 1, the conic is a parabola. If it's less than 1, it's an ellipse. And if it's greater than 1, it's a hyperbola. And here are these generic sort of diagrams of those conics. And below them, their eccentricity values. And PF, as we're seeing in this left-hand diagram, is the distance from a point on the curve to the focus. And dP is the distance from a point on the curve perpendicularly over to the directrix. And so that's PF from the point to the focus, PD from the point to the directrix, and those are the two distances that we're going to look at in order to calculate our eccentricity value. And as you might recall from the definition of a parabola, the parabola is the collection of points, or the locus of points, where those two distances are equal to each other. So we shouldn't be surprised to see an eccentricity value of 1 there. In the middle, for our ellipse, the denominator is going to be larger, so that PD from the point to the directrix distance is going to be longer, causing an eccentricity value less than 1. And the diagram on the right for the hyperbola gives us an eccentricity larger than 1. So you'd have to kind of root around in that diagram there. Excuse me, I don't want to spend too much time looking at those, but you can certainly refer back to those. Here I've done some highlighting on these notes already. The pole for all of these curves that we're going to look at on the polar plane, the pole is going to be a focus. A parabola only has one focus, but an ellipse and a hyperbola each have 2 foci, but one of the foci will for sure be at the pole. And P is going to represent the distance from the focus from the directrix to the focus. In other words, from the directrix to the pole. And the equations for these conics are a little intimidating looking, for me mostly because they look so similar to each other. But let me point out to you the 2 key differences between these 4 equations. In the top left, right at the top left part of your screen there, we see this equation has in its denominator a plus sign, and we're using the cosine function. To the right of there, this equation has a minus sign, but is still using the cosine function. The graphs below them, the one on the left, involving the plus sign and the cosine, is concave to the left, and on the right, we're concave to the right. So we're concave in the horizontal direction, which we've seen a lot when we're working with the cosine function. In this case, however, it's a little bit backwards, because this plus sign that we're seeing in the left-hand equation might lead you to believe that it's concave to the right or in the positive horizontal direction, but in fact it's not. Now, my students get to use a formula sheet which has these diagrams on it, so that makes it considerably easier for them because they don't have to commit all of this stuff to memory, but they do still have to be very familiar with how to use this formula sheet and reference this information quickly and accurately in order to be able to use it well. Farther down the page, we're seeing In the denominators for these equations, the plus and the minus, and these equations involve the sine function, and there is concavity downward and upward. Now remember, if either one of these, if any one of these four graphs turns out to be a hyperbola, for example, in the bottom left here, if this turns out to be a hyperbola, then there's going to be another directrix, and there's going to be another curve that goes over here. So to say that this graph in the bottom left is concave down isn't entirely accurate. Only a portion of a hyperbolic graph would be concave down. The rest of it's going to be concave up. So graphing these is going to be a little bit tricky, and we'll talk about some strategies for how to get oriented and organized a little bit later in these notes. Let me get rid of these additional markings. All right. Regarding symmetry, the equations that involve the cosine function, those were the first two graphs. They have symmetry with respect to the polar axis. So we see the polar axis passing through here, and whether this shape in the top left or the one in the top right is a hyperbola, a parabola, or an ellipse, we are going to have symmetry about the x-axis or the polar axis. The equations involving the sine function are going to have symmetry about or with respect to theta equals pi over 2, or the y-axis, or the vertical axis, however it is you want to refer to that axis on the polar plane. I usually call it theta equals pi over 2 when I'm on the polar plane. Now in these equations we have the challenge of identifying which conic is, or would be graphed as a result of graphing these equations. And remember, we can make that determination based on the eccentricity. So let's see what we can do. I think I'm going to keep using blue. Let's make that line a little thinner. And the first thing I'm going to do is to remember that this is equal to EP over 1 plus E cosine theta. So I'm using the plus sign that's here to guide me and put the plus sign here. The cosine function is here, so I'm putting the cosine function here. And what's going to guide my next maneuver is this 3. I know that I need, for my standard form, I need that 3 to turn into a 1. So I'm going to factor a 3 out of the entire denominator, which is going to look a little unusual. I'll leave the 6 in the numerator for the moment. Let's factor a 3 out of these two terms in the denominator. All right, and remember that you can double check to make sure that you factored correctly by distributing or multiplying the 3 back out, and that would work if you did that in this case. The next thing I'm going to do is divide the 6 by the 3, so I'm going to reduce right here so that the 3 is entirely gone from the denominator. So we're left with a 2 in the numerator, and in the denominator 1 plus 2/3 cosine theta. What I learn from this equation now in standard form is that the coefficient on the trig function, which is cosine in this case, that coefficient is my E value, my eccentricity. There it is, and since my E value is less than 1, I know that the resulting graph would be an ellipse. So let's jot that down. Describe the location of the directrix. Well, first of all, we can learn by using this value of 2/3 from the eccentricity. We can now take and incorporate that into the numerator, because our numerator is e times p. And I now know what my e value is. So I'm going to use those three components. I think I might even stay in red because I'm using those three elements to write that EP is equal to 2, right? EP is equal to 2. And we now know that E is 2/3. So 2/3 times P is equal to 2. And if we multiply both sides by 3/2, so multiplying both sides by the reciprocal, we get a p-value of 3. Remember that the p-value is the distance away from the focus, which is the pole. It's the distance from the pole to the directrix. Now the only other question is a distance of 3 units in which direction? We're going to scroll up to the previous slide, knowing that in the denominator we had a plus sign and a cosine. We can see in the top left corner, in the denominator, the plus sign and the cosine, which means we are concave to the left. And then let's come back down. If my curve is going to be concave to the left, that's a very squiggly horizontal axis. That's a little better. So remember, the origin is going to be the pole, the origin is going to be the focus. This curve is going to be wrapping around that focus, around the pole. This portion of it will be concave to the left based on what we saw on the previous slide. The directrix is, as I like to call it, behind the curve, and in this case, this distance, the distance from the focus to the directrix, is our p-value, which we just determined is 3. So now we could write an equation for the directrix. It's a vertical line. Every point on this dashed line has the same x-coordinate. They all have x-coordinates of 3. So the equation for that will be x equals 3. There we go. So from this one little equation, we've extracted a pretty good amount of information. I've used more than my allotted space on this page though, so I'm going to go down to the next page and see, let's see, we could work this one also. That has a plus in the denominator and the cosine function just like the one that we worked. Let's see on the next page. Let's talk about graphing, and we'll also do a similar process to what we did on the previous page in order to gather some information about this equation. So for graphing purposes, this set of pre-printed notes is instructing us to write the equation if necessary in one of the standard forms, which we're going to do because that's the easiest way to get an e value and a p value so that we know what kind of a conic we're working with and how far away the directrix is going to be from the pole or from one of the foci. And then on page 911, which I'm not going to reference, there are some additional steps in there regarding the graphing process. I'm not going to go too intensely on the graphing process, but once we know something about the type of symmetry that we would be looking at in this particular graph, we could select some appropriate theta values, plot some points, and then utilize symmetry in order to draw our graph or to choose it from a multiple choice lineup. So let's get into this one. Get that right to the top of the screen so we've got some room to work. I'm going to continue, I think I'll switch over to black, and the first thing that I know I need is for this 5 to become a 1, so we're going to do a little factoring. R is equal to, let's leave the 12 in the numerator, factor the 5 out in the denominator, so we end up with 1 minus 3/5 times cosine theta. In the previous problem, we were able to very cleanly divide or reduce the numerator with the factor that we pulled out in the denominator. This one's not so nice, so what we're going to do is end up with a 12/5 in our numerator, and we know that we're going to have to contend with that later as we're calculating our p-value, and in the denominator, 1 minus 3/5 cosine theta. The 3/5 is our e value. And then we'll utilize the fact that our numerator contains EP, and we'll combine that with our e value in order to calculate our p value. Coming down onto the next line, EP is equal to 12/5. Our e value is 3/5 times p equals 12/5. Multiply both sides by the reciprocal of 3/5. So p is going to equal 12/5 times 5/3. The 5's cancel. 12 divides by 3. That's very nice. We get a p-value of 4. So I'm happy to know this value. I'm happy to know this value. The e value being 3/5, which is less than 1, tells us that we're working with an ellipse. So if you wanted to, let's see, I could go back a line and put in a note that since this is less than 1, that implies an ellipse. If you can squeeze that into your notes. Excuse me. And this is the distance from the focus / pole to the directrix. Let's talk about the orientation of our ellipse. Maybe a good way to do that would be to come back up right next to the original equation and put a couple of little notes there. Maybe -3 cosine theta implies negative, maybe not implies. How about we'll just put an arrow and we'll say that the negative, well, we really want to combine these two things together. Negative and cosine, therefore, I think you know this already because you can picture the previous page. I can, my mind works that way. But if yours doesn't, referring back and seeing the negative and the cosine in the top right corner means we're concave to the right. We can also see the location of the directrix there. X is going to equal -p. We already know what our p value is. So this is getting easier. I like this. Do I have any more room over there? I do. Concave right. I was able to squeeze that in there. It's not very pretty, but that's what that says, concave right. Let's go down here onto our graph and start putting some of these components in place. You could also put, if you wanted to try to fit it in here, you could, otherwise we'll see it on the graph. The directrix we saw had an equation immediately of x equals -p, which equals -3. On our graph, let's go ahead and place that directrix right away. So there's the pole, and then 1, 2, 3 units to the left of there. Maybe I'll put a mark, and you know, if you had a straight edge or something that you could use, I got nothing. Here's an envelope. Let me try to put in a vertical line here, dashed to represent our directrix. So accurate, so necessary to be that accurate, right? Okay. Oh, that was returned from someone. I should try to send that back to them. Later, okay. So our directrix, you could label this as x equals -3 if you like, That's not a polar equation, by the way. That's a rectangular equation, x equals -3. And we know that our ellipse is going to be, at least part of it, is going to be curved or cupped or concave around the pole, which is the focus. What's the rest of this graph going to look like? Well, I don't actually know how far out it's going to go, but remember that this ellipse is going to have symmetry about the horizontal axis, the x-axis, the polar axis. So if we could figure out some points, maybe, that are on the ellipse, why am I drawing those points there? Those aren't convenient. Well, this one was. This is aiming in the direction of pi. And then maybe pick one in the direction of 2 pi over 3. And then maybe 1 pi over 3. And then pi over 6. I don't want to do pi over 12, because that's not very fun, but maybe we could still do 0. And then we could take all of those points, reflect them over the horizontal axis, and we would have a very nice, complete, at least approximation of what our ellipse would look like. So would it be nice at all for us to plug some theta values in there? It would be, but it involves more arithmetic than I really care to do at the moment, but I trust that you can either do it longhand or use a calculator, plug some theta values in there, excuse me, and generate some R values. And remember that once you do that, I'm losing my voice, I don't know why. Sorry. Once you do that, you're going to be plotting these points with a radius and a theta value, r comma theta, aiming in the direction of theta, moving forward or potentially backward a distance of r in order to plot your point. And this is very much the same kind of a process. You will need to factor out a 2 from the denominator, reduce that with the 6 in the numerator, calculate your e value, calculate the p value, figure out the orientation of your conic section, and then start doing some graphing. Try to follow this process as a model. And you could go back through here and rewatch a portion of the video and see what you think would be a good way to sort of enumerate the steps. I would say that this is a really key part of the process. You could write down some notes about the orientation of your conic right away. And you could even have drawn a little sketch of it up there. We know that it's going to look something like this. Okay. I drew too much of the curve there. I don't want this part there. There we go. So we know it's initially going to look something like that. You could have also put in a bit of your directrix there, and then we wrote a note down over here about the actual equation of the directrix, x equals -p. If you had done that first, then you would not have had the -3 there yet, or you wouldn't have had the 3 as the p value. But knowing that x equals -p, that would have already been written down on your paper for you. And then the next part of the process would be this part where we're going through in order to generate our e value. And that helped us to determine what kind of a shape we were working with. In this case, it was an ellipse. And then we went through and used our numerator, which was EP, and that helped us find our p value, which gave us the distance from the pole to the directrix, and it was that p value then that allowed us to fill this in as equaling -3. And from there, we did a little bit of graphing, and then you would maybe make yourself a little table or an organized list, plug in some theta values, calculate some r values, plot some points, and then don't forget to use the symmetry of any one of the orientations of these graphs in order to get a little bit of a buy one, get one. You get to flop half of these points over the x-axis. Same process there, same process here. So I hope my helping you get started on those processes and walk through and get organized is helpful to you. and I look forward to seeing you in future sections. Thanks so much.